Hello, my name is Tom Blount, and today I am going to be talking about our work on the concept of possible provenance. The motivating question for this work was we wanted to investigate how provenance is currently captured. Often this can be a relatively intense, resource-intensive process in terms of time, technical resources, and social resources, and we wanted to investigate what were the consequences if these resources were not available. Is there a way to mitigate it, for example? So to this end, we have categorized a number of ways of capturing provenance at the current time. We propose a concept of possible provenance, which I shall talk about in more detail shortly. We show how this can be put into practice with a small-scale viability test. And we propose a number of metrics for refining this approach further and go on with a plan for future work. So to talk about provenance capture, we created a simple taxonomy of different methods for capturing provenance, primarily looking at ways in which we can capture provenance by observing it directly, and ways that we have to fall back on if we don't have those resources to directly observe the provenance process. So to give a quick overview of this, when looking at observed provenance, there are two main approaches. We can either consider in situ provenance, where the provenance is recorded as it happens. This is the case in a lot of scientific workflow frameworks and pieces of software, in which every action a user takes is automatically recorded as part of the provenance chain. However, there are a number of different ways of doing this without directly recording the provenance itself. For example, we can create a post hoc provenance chain based on logs of the user actions. So while the provenance is not recorded directly in situ, it still records and observes the user's actions in a number of different ways. And this can be done through creating snapshots of the operating system throughout their work that is then replayed and the provenance rebuilt from that, or by looking at more contextual clues such as user annotations, or even external resources such as GitHub logs and rebuilding the provenance from those interactions. However, when we look to unobserved provenance, what happens when we don't have the facility or the resources to fully observe the system? So there are a number of different approaches to this. Either we can simply try and record the elements of the provenance that we're able to, but with some sort of uncertainty value, deliberately and directly recording into the provenance metadata that these are unsure or uncertain observations, and we can attribute some value to that. Alternatively, we can try and infer the provenance that is happening, again from these logs, for example, in a way that we cannot be directly sure that this is the provenance that is correct, but we can try and infer it through patterns of likeliness. And we can also consider this concept of possible provenance. Rather than trying to predict the correct provenance path, we can simply announce a number of possible provenances, such that any of them could be the true provenance path, even if we cannot tell for 100% certainty which is which. So what could this approach tell us? Well, let's look at it with a simpler example. I'm going to use Connect 4 as a nice working example. Connect 4 is a popular board game, but if you're not familiar with it, players take it in turns to place coloured discs in this sort of grid, and the first person to get 4 in a row, whether horizontally, vertically, or diagonally, wins. So can we model the possible provenance of a game of Connect 4? So let's start off with a 3x3 grid. This will make the diagrams a lot clearer. Obviously this means that neither of the players will actually be able to win, but for this that doesn't actually matter. We're just interested in the sequence of moves. So we'll begin by generating a full game of this. Again, it's not optimal play. This doesn't matter because we're only interested in the sequence of moves rather than how good these players are at Connect 4. So if you take a look at the diagram below, this is what we will say is the true provenance. But again, what if we don't actually have the resources to fully observe that game? It becomes something like this. We can say with certainty that we know what the start state is, because either because we've been able to allocate resources to that, or just because we know the state that a Connect 4 board always starts in. And similarly, we know what the final state of the game was, again, either because we've been able to attribute resources to that, or because, again, this is the state that the board is currently in, so we're able to observe it. But we haven't been able to observe any of the states in between. So can we calculate from this the possible set of provenances, And can we do anything to look at which one of those is perhaps the most likely provenance? Well, with answer set programming, we can try and model the valid state transitions between all of the different states in our model with a number of different rules. And then we can use abductive reasoning to infer or determine the logical consequences of those rules. So here is, for example, a very, very simple model, or at least part of the very, very simple model that makes up this Connect4 rule set. First, we begin by saying that the contents of any cell are either empty, red, or yellow. We can then say that there is a transition between two states of play if there is a time, a start state, and an end state, denoted in this case by cell 0 and cell 1, and cell 0 prime and cell 1. So the first part of this rule is to say what defines a valid transition. So we can say cell 0 must start empty, cell 1 must conform to the contents that we set up previously, and cell 0 will become red if the time is a modulo 2 is 0, so if it's an even timestamp. Similarly, we could have a different rule that says if it's an odd timestamp, then it must be yellow's turn. However, we can improve this model by adding some additional constraints which will reduce the size of our final state space. So we can say that we will only consider a transition as valid if there is a path to the starting state of that transition. And likewise, because we know the ultimate end state that we are trying to aim for, we can say that we will only consider states or transitions between states that lead towards that end state. This code is all available on our GitHub, so please feel free to download the Jupyter workbook and see this working for yourself in practice. This brings us to the outcome of the model. Not just a possible provenance, but all of the possible provenances that could link our start and end states. The true provenance from our previous worked example is highlighted in red. This wouldn't necessarily be visible if we are utilizing this model in practice as a real working thing, but I've left it here just to highlight that it is present in the set of possible provenances. This model can get very, very complicated, and certainly visualizing it can get very, very complicated as we increase this state space, which is why I've used a 3x3 grid. But it is possible, for example, to visualize a full game of Connect4 between two end states as such. So now that we have this output from the model, what can this do for us? Or rather, what can we measure about it that will help us refine this approach in future? So there are a number of things to do with the model that we can look at, for example, the specificity of it. How closely does our model reflect reality? How closely do the transitions map to real-world equivalences, and also to the final provenance that we want to output in the end? Similarly, correctness. As I mentioned before, our true path is highlighted in this in red, and we can do this because we know the true provenance as well. So this is a good argument for example, some test modeling when you have the full range of resources at your disposal to ensure that your model is accurate. A number of other concepts from the output of the graph that we can look at is, for example, the overall structure of the graph. If there is one node that every possible path passes through, then we know for certain that, as long as our model is correct, this node is definitely part of the true provenance. Likewise, we can look at accuracy and variance. By accuracy, I mean if we take each possible provenance path and match it against our known true provenance, we can determine the percentage of nodes in each path that map to the true path. Likewise for variance, if we look at every node in the true path, we can see how many other paths pass through it. And as an example, here are two graphs of the accuracy on the left and variance on the right that for our worked example. Now, these metrics in particular aren't helpful if we don't know the true provenance, but they're a useful way of looking at our model and seeing how closely our model relates to the truth, and if we can say with relative confidence that our accuracy or variance rate in a particular instance is sufficient for a user's needs, then we can say that our model is currently satisfactory for that case, and then we can apply that model in practice. So moving on to another interesting upshot of this work, the idea of known capture points. Let's imagine that in our previous worked example we have the resources to take one additional snapshot, and we randomly allocate that in the middle of the game of Connect4. As you can see from this graph on the right, this massively reduces the state space because by splitting the problem in two, start and middle to end. And in fact, the first chunk of the problem, we can now say the possible provenance is the true provenance with 100% certainty, because there is only that one valid path between that start and the middle. This raises a number of interesting questions. How can we define what is the best of these snapshots to capture? How can we best allocate our resources as a result of that? And this moves us on to some of the interesting use cases of this. Possible provenance by itself is very interesting in terms of when we want to capture provenance, where we want some idea of the provenance that has occurred, but we don't actually necessarily care about the exact chain of resources. As long as we know that certain steps happened, for example, it may not matter which order that they occurred in. However, the most interesting use of this, in my opinion, is using this approach to augment other modes of capturing provenance, particularly observed cases. By looking at the possible provenance graph, we can then determine where is the most appropriate and most efficient places to allocate our limited resources to reduce the state space even further and make the most accurate and efficient capture of provenance with our limited resources. One case that this approach would be bad for example, would be live security, partly because possible provenance in this case revolves around creating an accurate model of the system, whereas defeating the security of that system often involves breaking or subverting some of those rules. As far as future work goes, obviously we can expand the categorization framework further and make it more in depth. We can also look at modeling real data, so rather than using this toy example of Connect 4, we can take some existing data scenarios and look towards modeling those and coming up with the possible provenance for it. Likewise, we can further develop the KCP detection, really focus in on those known capture points, as well as, importantly I find, conducting a human study to determine which elements of possible provenance are most useful for data managers, data controllers, and data auditors. So, just quickly elaborating on this part of the future work, in the same way that we model our game of Connect 4, there is no reason why we couldn't model a database in this sense. But instead of colors of cells, we have different operations that could be used on it, and similarly we have our start data set and our end data set, which leads to a sneak preview of some future work that we're currently working on, where we can have a similar looking graph but for actual data rather than just a simple game of Connect 4. In particular, this highlights a number of interesting changes, for example modeling different types of transition based on different operations that could be performed on a database. So, in conclusion, we've categorized a number of means of provenance capture. We proposed the concept of possible provenance as a whole and talked about how it can relate to and possibly even augment observed provenance capture. And we show the viability of it with a small-scale example, but display our future work plans for going on to enhance this further. And we've proposed a number of metrics for refining and describing possible provenance at large. So thank you very much for listening to my talk. If you have any questions, I will be happy to answer them, and if you'd like to get in touch further down the line, my contact details are on the screen now. Thanks very much.